Hi, this is Adib Islam presenting on behalf of Group 6. The topic for this discussion was learning from noisy label, a survey. So I will present our discussion from here forward. So our first topic of discussion was, in the absence of clean labels for a validation set, how do we evaluate the model? So one member suggested that we could use unsupervised techniques. For example, if we take the non-deep learning approach, we could use classic clustering algorithms to to basically cluster different classes of labels together. So in that sense, we can generate some clean labels. Another member suggested that if we wanted to take the deep learning route, we could use autoencoders to cluster the correct labels together. And the reason we thought that these techniques would work is because these techniques would exploit the latent pattern within the dataset. Thus, any random noises embedded in the dataset would be removed. Then one member brought up the topic, what if the noisy labels are not random? What if there is some dependency with features and noisy label? So this basically is an example of a complex noise which was addressed by the survey. So like, according to the survey, we could train some dedicated noise network to estimate the label corruption transition matrix to generate cleaner labels. So that could be an option, but then another problem could be, what if we don't have any clean data to train such dedicated noise network? So this is an open topic for discussion. We would like to hear what you think about that. For discussion two, the topic was, how do we train a data set which is missing some labels? So far, we consider data set which had correct labels and also incorrect labels spread out. But what if there are no labels to begin with? So in that case, one member suggested that we could remove those data examples. Remove the data examples which did not have any associative labels. But the problem with that would be we would throw out some data examples. So basically, we are only partially exploring the dataset. We would want to exploit any and all information available in the dataset, so we want to explore the entire dataset. So another member suggested that maybe there could be some unsupervised or semi-supervised technique for label generation. And in fact, after some research, we found out several techniques which actually does label correction and also label generation using this kind of techniques. And I will present some of those papers right now. So the first paper that I would like to present is meta label correction for noisy label training. This was published by Microsoft Research in 2021. So the main idea here is, in sample selection, we usually throw out, not throw out, but we are not utilizing labels that we consider to be noisy or weak. But instead of throwing it out, this paper suggested that maybe we could recorrect noisy labels. So the way they're doing it is by taking a meta-learning approach where the meta model is a label correction network which produces correct labels. And the main model uses the corrected labels for training. By main model, I mean the target model. The main model uses the corrected labels for training and updates its parameter on a clean data set for evaluation. Both meta model and the main model are trained jointly by solving a bi-level optimization problem. However, this optimization problem is computationally very taxing, so a k-step look-ahead stochastic gradient descent is used to address the complexity issue. So the advantage here is, unlike sample selection, or also if you're reweighting techniques where noisy labels are downweighted and are removed, this technique leverages the weak evidence present in noisy labels by generating corrected labels. So it ensures that we are fully exploring the dataset. Another advantage is it does not make any assumptions on the label noise. So if you might have noticed in the survey that some techniques assumes that the noise is only so some noises are instance independent. That means that the feature there is no relation with the corruption of the label and the data features. So this model does not make such bold assumptions. Therefore, this works well for instance-dependent noise. The result is it outperforms the state of the art for both image and text classification, captures data-dependent label corruptions, and is robust against serial label noise. The second paper I would like to discuss is co-learning, learning from noisy labels with self-supervision. So the main idea of this technique is to use a shared feature encoder with two exclusive heads. One head will perform self-supervision to exploit feature-dependent information in the data through a measure that they called intrinsic similarity. The other head is a classifier which performs supervised learning and learns from label-dependent information. A structural similarity loss is utilized between the two heads to regularize the classifier and avoid bias caused by noisy label. Basically, the idea here is we are looking at the same features from two different perspectives, and then we try to minimize the loss so that both of them converge. The advantage here is that previous techniques exploited this trick called small loss trick. Basically, the idea was if the loss is small, the label was considered to be correct. If the loss was large, it was considered to be weak or noisy label. But in order to do that, we need noise rate and other carefully chosen parameters which are not available readily in the real world data set. And in fact, this was another discussion point that I didn't bring up here that we had. So some of our members were asking how do we actually, how was the noise rate in some of the data set figured out? Because, for example, if we are gathering data from a crowdsourcing method or something like that, it would be like almost impossible to figure out the noise rate, right? So most real-world data sets are like that. And techniques which exploited small loss rate, and these are techniques are many, abundant. These techniques would not perform well in real-world data because we don't have this noise rate information for real-world data. Since this co-learning technique does not need the small loss rate, it performs really well in real-world data, and it achieves robust training without any trivial tricks. So co-learning outperforms other co-training based methods. So for example, MentorNet or co-teaching, and provides a new perspective to leverage self-supervised learning to assist robust deep learning. We particularly chose these two papers to reflect back on our discussion, where where we talked about how we could generate labels when labels were absent, and how would we evaluate when clean data was unavailable. So these two papers kind of gave us some answers, but we would still like to hear from you what you have to say, what you have to add. Thank you so much for listening. Have a nice day.